Yes.
Okay, as said, my name is Matty. I work here at the NASA Johnson Space Center in Houston, Texas. I always like this picture here of the Earth. It's really just a nice demonstration of the scale of kind of our planet and where we are. You can see the storm there kind of in the middle. I always think that's really, really cool. The great big cumulonimbus cloud reaching up to the stratosphere. And you can see also, I always like the way the reflections happen on the planet when you're looking out from space. You can see this kind of very large reflection, right? I mean, in reality, that reflection bright spot is hundreds of miles wide, but it wouldn't look like that if you're on the surface. You know, it behaves as a fractal, which I think is really, really interesting. And then also, I always like to point out to people just the little tiny sliver of atmosphere there really kind of, again, demonstrates how fragile and how kind of tenuous, you know, our hold on this planet is and how careful we have to be to kind of take care of this. So as stated, so I grew up in Middle Tennessee. There's a very large Air Force base actually right here below this reservoir, Woods Reservoir here in the middle of Tennessee, called Arnold Air Force Base. I grew up water skiing, backpacking, rafting, rock climbing, and mountain biking. There's a picture of me with my mountain bike in the mid-90s there, looking very cool. And I have a BS in aerospace engineering from the University of Oklahoma and an MS in astroparticle physics from the University of Houston, Clear Lake. A few of the things I've worked on. So as stated, I've worked on the space shuttle, the ISS and the Orion programs, and then back on the ISS again. And so one of my specialty areas of expertise is environmental control and life support. So those are the systems that scrub the air, the systems that clean the water, the systems that make it so the water is drinkable and the air is breathable. And then also the trace contaminant removal. So if you lock a human being in a closed environment, your body is always outgassing things such as methane, such as ammonia, that have to be scrubbed back out of the atmosphere. And then we have sensors that we use in that atmosphere to kind of tell us what's in the atmosphere and how we're doing in keeping the atmosphere maintained. And we use those sensors to kind of measure the different constituents and also what we call the trace that's in the atmosphere. And then we're planning and designing kind of next generation systems for systems that we're going to take into what we call cislunar space, that is the space between the Earth and the Moon. And so out into space, or going out to missions around the Moon, and then out into deep space as we're expanding out into Mars, etc. Other things I do, I like to kind of keep busy. I am a scuba diver. I'm a PADI dive master. I'm currently certified in 12 different forms of diving, including ice diving, which you can see there's a picture I took of one of my buddies there. We are under ice in Banff, Canada. It's a lot like spacewalking in that you have to go in through a very, very small hole, and the only way back out is to find your way back to that hole again. And you're wearing a lot of gear and you're fully dependent on this system for sustaining your life support. I also run. I've run a bunch of full marathons and half marathons. I am a private pilot. I am a racing and driving instructor, and I like building all kinds of things. I like to kind of maintain curiosity about how things work, about how things are put together. And then a bit of my personal philosophy. I like to try to remember that, you know, the world was not built by atomic supermen. Anything that somebody else knows, anytime you see something, you think, wow, that's really cool. That's something you can do, right? I mean, these things only exist because somebody put in the time and the effort to learn how to do it. And then similarly, any machine, invention, organization, or system exists because somebody envisioned a goal beyond themselves, envisioned something bigger than themselves, and set about forming a team, forming partnerships, educating themselves, helping other people get educated, and then setting about to achieve and kind of chase that goal. And that's a big part of kind of, you know, what makes life go around, and in my opinion, what makes us all stronger working together. So we're going to be talking about some astrophysics, some basic physics as well, but these are challenging ideas. And I like to tell people, you know, there's not a test on this stuff. These are big, big ideas, and these are ideas that even very smart people with PhDs still struggle to get their heads around this stuff. This is the edge of our human understanding of the universe. And so this is, you know, if you don't feel, you know, if you don't immediately grasp this stuff, there's no reason to feel bad about that. There's no, you know, this is very out there confusing stuff. But similarly, you can learn these things, right? This is, as with all information, These are things that you can learn and master if you just expose yourself to them, if you just practice repeatedly. So the human scale, we are used to thinking and dealing with the world on what we call the human, or what I like to think of as the human scale. So these are things that, you can generally touch, you can generally sense with your five senses, the way that we perceive the world. However, in reality, almost none of the universe exists on the human scale. Almost everything is much, much bigger, like galactic scale, or much, much smaller, being like atomic scale. Only a very small fraction of existence is at the human scale. So in this case, the human scale represented by the orange slices there, right? We all know what an orange slice is like. We've all seen one, held one, smelled one, eaten one, versus a galactic cluster there on the right. And you can see there's a lot of similarities. There's similarities in the color, there's similarities in some of the arrangement, but they're very, very different things. And they're actually beholden to a similar but different set of physics as we generally perceive it, in that the physics that is guiding and governing galactic phenomena don't necessarily make sense to us on our immediate human scale. They don't necessarily apply the way we would think of them in the day-to-day of our daily lives. So unification, the process of understanding the world around us, the process of science in general, comes down to what we consider unification. So that's taking a lot of disparate things, taking all the different things that we see and observe in the world around us, and then grouping them into common phenomena, and realizing that things that we think are very different and diverse are actually governed by the same set of rules, and in a lot of cases, different manifestations of the same basic phenomena. So Isaac Newton in the 17th century showed us that motion and rest are the same things. That's effectively what Newton's laws of motion are saying, that everything depends on your reference frame, right? Right now you are sitting still in a chair, but you are moving extremely fast relative to the spinning of the earth. And then the earth is moving extremely fast around the sun, and the moon is moving around the earth. And so depending on where your frame of reference is, you're actually moving pretty quickly compared to some other things, even though you're expending very little energy to do it, and you're kind of just sitting there as you immediately perceive it. Similarly, James Clerk Maxwell in the 19th century showed us that electricity, magnetism, and light are the same things. That's why I can be talking to you here over, thousands of miles, because we are able to turn light into an electrical signal, transmit that a long distance, and then back into light at your end, back into a visible display at your end, and a audible signal at your end. So these are things that we use every day in our everyday life. And that's, everybody is familiar with an electric light bulb. Everybody's now familiar with a digital camera or digital display, but that all exists because of Maxwell's laws. And then Albert Einstein in the 20th century showed us that matter and energy are the same thing. A lot of people are familiar with the equation E equals mc squared, and also showed us that space and time are the same thing. And that one is a bit harder to grasp, even though that is also something that we deal with on a daily basis. So the distance between objects and what we perceive as time are actually the same things. And we as human beings are being pushed forward kind of on this unstopping treadmill of time, where we can't stop time and we can't go backwards in time, but we're not exactly sure why. We're not exactly sure why time is happening. We're not exactly sure why this second is different from that second, is different from that second, but we can't go back, right? You can't navigate through time quite like we navigate through space. But if we go to the physics equations that govern such things, we find that they are the same thing. We often talk about somewhere as being an hour away, or several miles away. But in reality, when you travel through space, you are also traveling through time. And so those things can be unified in physics. But again, that's getting kind of to the edge of what makes sense in our day-to-day human experience. And then a big part of this that I think is very important for students, and I think is very interesting about what we're going to talk about here, is the future is wide open. This stuff is right on the edge of human understanding, but also in a lot of ways that makes it much more accessible, which I really find exciting, is that this is stuff that is right there. You could be the next big step in our understanding of the universe, in our understanding of the world as this stuff applies to it. And so, this is not stuff that was discovered by dusty old men hundreds of years ago. This is stuff that people are discovering new stuff about on a daily basis, and things that you could be one of the next big contributors to. So relativity, as I said, almost every quantity in which we deal with as a human on the human scale is relative. So if you think of cars on the highway, right? You're driving at 60 miles an hour. If there's another car driving next to you at 60 miles an hour, you see each other as standing still, basically relative to each other, right? You could reach out and touch their hand. You could reach out and shake hands with them if you didn't crash the car. You could reach out and shake hands with them and it wouldn't hurt, right? And you could, you see them as still relative to you. Similarly, if there's another car coming the other way at 60 miles an hour past you, you see them as moving very fast. You see them as 120 miles an hour relative to you because they're moving the other direction at 60 miles an hour. And so this is key because the sun, Earth, the galaxy, everything is moving all the time. And as we will see, when you get to galactic motion, when you get to interplanetary motion, those rules are similar to the model of the two driving cars, but are actually start to get very different. Speed of light. The speed of light is not relative. And this is another thing that Einstein showed us. So Einstein's equations dictate that the speed of light is constant for all observers in all reference frames. And so this refers to the speed of light in a vacuum. Light does slow down when it's moving through media. That's why we get light refraction through water, through a lens, etc. But light in a vacuum is moving at a constant c, and that is not dynamic. So a light particle is not experiencing, a photon is not experiencing space and time like we are. And that's really weird to think about. But similarly, light is not dynamic. If you're running at the speed of light and you turn on a flashlight, it's not like the light's going to go out of that flashlight at twice the speed of light. We're going to talk about that. And so because of that, nothing can go faster than the speed of light in any reference frame. And again, these are things that are right on our edge of understanding, but the things that our math and physics tell us right now. And so that seems to create a fundamental problem, right? The question of the dynamic, again, with the model of the two cars. So if you have car A traveling at 70% the speed of light, which we would call 0.7 c, and car B is traveling at 80% the speed of light, which we would call 0.8 c toward it, then the example, again, of the two cars driving 60 miles an hour would tell us that the speed between the cars would have to be 0.7 plus 0.8, which would be 1.5, which is faster than the speed of light. Well, we just said that nothing can travel faster than the speed of light, right? So that seems to create a fundamental paradox. And this is something that I hear people talk about sometimes when they're just learning this stuff. However, that is not a problem, because when you actually work with these equations, you find that as an object approaches the speed of light, time expands, time slows down, and space contracts. So time is expanding, it's slowing down, and space is contracting. Space is actually getting smaller relative to an outside observer. So because time is expanding and space is contracting, both cars are going to be observed at moving at sublight speeds relative to the other car. And so you can do that with math, right? So again, typically we would assume that this is this top equation here, that u prime equals your velocity A plus velocity B, which is 1.5 c. However, that is not how relativity works. So general relativity actually is governed by this equation. And so when you do that, you'll find that relative to each other, the cars actually see each other moving at 0.23 c, 23% the speed of light, which is weird because this is slower than either of the cars' individual speeds relative to an outside observer. So as the cars are actually approaching the speed of light, again, time is expanding and space is contracting such that they are slowing down relative to each other. And as they approach the speed of light, their speeds will slow further until they actually equal 0 as they reach the speed of light, which is, again, really strange to think about. So space-time, as we said, per Einstein, space and time are the same thing. As an object moves across space, it also moves proportionally through time. As an object approaches the speed of light, time expands, time slows down, and space contracts relative to an outside observer. And then gravity influences space-time. but we do not know why. We actually don't fundamentally understand what gravity is. We can observe it. We have equations that allow us to approximate the effects of gravity, but we don't actually know why gravity happens, which I think is really inspiring to me, right? That with all of our hundreds of years of scientific and physics research, we still can't answer the basic question of why does something fall when I drop it? But we do know that with gravity, again, time and space are bent. Space-time is bent by gravity. And as the reference frame approaches an object with mass, time expands, time slows down, and space contracts. So the people on the space station are moving a little bit faster in time because they're away from the planet, but they're also moving slower in time because they're moving much, much closer to the speed of light than we currently are sitting here on the planet Earth. And so then, as I said, so since gravity influences space-time, it sometimes helps to think of space as a flat, squishy surface into which massive objects sink. In the presence of an object with mass, space shrinks and time expands. And again, this is only really a model. This is a way of thinking about it in our kind of limited everyday human perception of the universe. But this is a model that people use often to kind of explain how space-time works. You can think of the big squishy surface here, and then as an object approaches the planet or the big object with mass, it falls into its space-time well, or it orbits by kind of skirting around like a skateboarder surfing around a bowl. So then escape velocity. If you think about the well, the big bowl that formed by an object with mass, you have to get relative energy to drive an object up out of that gravity well to escape from the gravity of an object with mass. And you can calculate the escape velocity for any massive object, but the escape velocity for Earth is approximately 11.2 kilometers per second, or 25,000 miles per hour, which again, even at that high speed, that is 0.000037 c. So that's still a very, very small fraction of the speed of light. So now black holes. Everybody likes to talk about black holes. And so a black hole is an extremely dense, massive object, usually a collapsed star, as we think of it. So the escape velocity, the speed required to escape the gravitational pull of a black hole, c. Therefore, nothing can escape a black hole once within the Schwarzschild radius. And that's also what we call the event horizon. This is one of the first pictures ever taken of a black hole, which was just taken in the last decade by a graduate student. And, you know, again, a person not much older than a lot of your high school students. And we now have taken several of these pictures of multiple different black holes, including the black hole that we now know is in the center of our galaxy. And it's possible that every galaxy is swirling around a black hole, a supermassive black hole in the middle. But as you look at the black hole here, you can see this shearing, this very bright spot around, and then the black, that is the event horizon, that is the radius within which the escape velocity exceeds c. And then inside of there, nothing can get out except Hawking radiation, which by Stephen Hawking. But that is a relatively new phenomenon, and that is something that we're just learning to understand. And when you talk about Hawking radiation, again, you're talking about literally the black hole splitting apart the fabric of the universe and spitting out a radiation that is composed of 1/2 of the fabric of existence as we understand it. So the Schwarzschild radius. Everything with mass has a Schwarzschild radius that you can calculate. But for a black hole, it's big enough that it really starts to matter. So at the Schwarzschild radius, as we said, nothing can escape, but also as the escape velocity starts to exceed c, time stops for an outside observer. Therefore, you can't ever see anything going into the black hole as we would currently think of it. And theoretically, past this point, time would start running backward to an outsider observer if we could observe it externally. But again, we don't really know what's happening there. This is right at the limit of our human understanding. So it's possible that yeah, inside of there is maybe a reflection of our own universe, just with time running backward. Maybe you can go into a black hole and then jump out of any other black hole in the universe at any other point, because there is no time and space at that boundary. And we don't really know. But again, we can calculate that when you hit the Schwarzschild radius, time stops right there. Time becomes infinite and space becomes zero. And then similarly, I mean, I like to, think about these equations, because just the way that you can kind of think about our relation to mass and space and time really gets shifted by this. Everything has a Schwarzschild radius. Everything has a radius within which it will form a black hole. So for example, all of the mass of the planet Earth has a Schwarzschild radius of about 3 centimeters. So roughly the size of a ping pong ball, right? So if you could squish all of the mass on planet Earth to down around the size of a ping pong ball, it would form a black hole. But would be a very, very dense object. And then the largest black hole we think we have observed is like 1.5 light years. And so thinking about 3 centimeters to a light year, it's just the amount of mass and the amount of energy involved in that is just mind-boggling. It's just way, way out there in our human understanding and our human perception of the universe. And then the detection of gravitational waves. Again, as I said, we just are just starting to understand what gravity even is, or being able to detect or try to describe gravity in a real fundamentally quantifiable way. But this was just done on September 14th, 2015. This was literally done while I was in grad school, which is something that I love doing part to students, because this is stuff that we are still learning about and finding out about every day. And this is right on the edge of our human understanding of the universe. And so again, this is stuff that you can contribute to. This is stuff that your students could be very much a part of, and could be, literally breaking ground in our human understanding of science and physics and the universe and energy in very fundamental ways. And that is right there, for the studying and for the learning. And I think that is really an amazing and kind of inspiring basis of kind of a lot of this stuff. And physics in general is that this is really stuff where it's not just, old guys up on the wall in black and white pictures. This is you. This is stuff that you can learn and you can study and you can be making giant strides in on a regular basis. So I've got some more stuff we can talk about, but I'll open up for questions. So kind of get the discussion going and see what you guys would like to talk about. Come on, guys! You guys got to have some questions. I mean, everybody always has weird questions about black holes, and they're not. And again, I mean, they are all fully valid questions. These are things that I mean, people like to talk about. It's things that's fun to exercise our imagination about. But then similarly, it's stuff that you can calculate. Yes, go ahead.
So my students have been asking me questions about what is dark matter and what is dark energy.
Okay, so dark matter and dark energy. Again, when we start to compile the governing equations of the universe, right? How we think the universe is expanding, how we think the universe is moving as a whole. The equations don't close. The equations don't add up. There is not enough mass and energy as we understand it to fill out those equations such that the movement of the universe makes sense. And it's not a little bit, it's a lot. Like, we can only account for 5% or so of the mass and the energy in the universe that would be required to make it move the way that we seem to think it's moving. A lot of that depends on what we consider the geometry of the universe, what we call topography, what we consider the shape of the universe, right? And so that's why there's a lot of study and a lot of discussion goes into what shape is the universe. But at the same time, even if you're just assuming very basic shapes of the universe, i.e. the universe is a ball or is a sphere, there's not enough matter and energy that we can observe to close those equations of motion. And so when we see that, then we start to talk about dark matter and dark energy, which is there are elements that would be required to make those equations work that we can't directly observe, right? That would be matter that we can't see, energy that we can't detect. And we believe that things are moving. I mean, really what those are is kind of holes in our understanding of the universe, right? Those are unfilled variables in the movement of the universe as we understand it. But it's also very likely that the limited equations that we are using to describe the universe aren't really enough to account for the movement of the universe as we're observing it. And again, that is something that's very accessible because those are things that we don't know yet, that we are just learning. We are just starting to be able to detect dark matter. There's actually a large detection array on ISS right now for looking for dark matter. And so, those discoveries are right on the edge of our understanding of the universe. But again, the fundamental answer is dark matter and dark energy are masses and energy that we can't see, but should be there in order to kind of close our equations as we currently describe the universe.
I have a question.
Yes.
Hi. This has been bothering me for a long time, but it's understood, I think, that gravity, since gravity is just a matter of warped space-time, and I heard it described as not even a force, why is there this necessity that we need to have a mediating particle like gravitons? Why should gravitons be necessary if gravity's not even a force?
That's a very good question. Yeah, is there a mediating particle of gravity? Again, so the LIGO detection, right? The LIGO detection, which happened on September 14th, 2015, which again, I know for most people on this call is not that long ago. It's not that long ago for me, but your students will think that is longer ago and will be less impressed by that. But, the LIGO detection showed us a wave of gravity, showed us that gravity moves as a wave. Before the LIGO detection, we had hypothesized, but we didn't even know that there could be such a thing as a wave of gravity, which we call a quanta of gravity, right? And so it's similarly, when we talk about gravity as a force, right? As we understand it right now, there's four fundamental forces to the universe. There's strong nuclear, weak nuclear, electromagnetic, and gravity. And really, we have started to unify electromagnetic and the weak nuclear into what we call the electroweak force. And so we started to describe those as a common force. And so we can describe the mediators of those forces, right? We can describe the subatomic particles and the quark interactions that make those forces go. We can also manipulate them. We can perform nuclear fusions and nuclear fissions. And we can't do it well, but we can do it such that we can release energy from the strong force, right, of splitting atoms apart. But we are just learning to do that. And similarly, we can manipulate a lot of the electroweak force. We can turn energy into light. We can turn light into energy. We can turn energy into magnetism. We can turn magnetism back into energy. But we can't do squat with gravity. We don't know what gravity's doing. We don't know what gravity is. Gravity is a relatively weak force, it appears to be, because right now, the electroweak forces in your backside are stopping the entire gravity of the planet from pulling you down through your chair, right? But again, we can't really do anything with gravity. We don't know how gravity behaves. And we don't know, as you say, we don't know if there is a mediating particle of gravity. Since we have detected gravitational waves with LIGO, we now believe that it behaves as a wave, and therefore it should have a mediating particle through space-time or some mediating quanta to describe it. but we're not really well equipped to describe what that looks like. And maybe our particle model, maybe our model of describing the universal forces in terms of particles is flawed. Right.
Okay. So what you're saying is then a graviton would be the smallest bit that space-time can be. Is that right? That would be like you could reduce space-time down to its, you said quantized. It would be like a particle of space-time.
Yeah, it would be.
That would be a graviton.
The unit of gravity. Yeah. Which again, I mean, you know, we talk about, you know, we can talk about the electric forces in electron volts.
Okay.
Right. We can talk about, we talk about mass in grams. We don't have gravities, right? We don't have units of gravity.
Right.
We talk about G's, but G's is only a proportion of Earth's gravity, which we kind of use as a baseline, right? That's not really a unit. That's just a ratio. And so we don't have a basic unit of gravity. And so, yeah, when you talk about things like gravitons, you're trying to model what a fundamental unit of gravity would look like. But again, we haven't really measured such things. We've only described that they should be there in order to fill the models out that we've formed.
Okay, that's very helpful. Thank you.
And again, so LIGO, I think.
Sorry, go ahead.
Sorry, go ahead.
I just had a question. There was a couple slides before this one, and it went by quick, and I'm wondering if it was my math or something, but it was the relative velocity of the two objects at 0.8c and 0.7. Yeah, that one right there. Are we dealing with the sign convention here? Or why is there no negative in front of the negative hc? Because I teach this to my kids and I got a different answer, and I'm wondering if I've been screwing up all these years.
So, yeah, in this case, you're looking at it as a scalar, not a vector, right? So that's why.
It's
right. Well, you've got, so if you've got 0.8 minus 0.7, so that there's one is moving one way and the other is moving the other way. So in this case, the 0.8 is positive and the 7 is negative, right?
So that is a vector.
Right, but isn't it VB minus VA? So wouldn't the negative negate? I mean, I've been doing it one way for longer than I want to admit if I've been doing it wrong.
Yeah, I'm trying to think. I will think on that and get back to you. I try to refrain from doing math in public because generally it gets messy.
I understand that.
But yeah, that's a valid question. I'll look at that and I'll get back to you.
Okay, thank you.
Sorry, now I'm looking at that. Anyway, sorry, other questions. Well, I was going to say, so the thing that's interesting to me about the LIGO detection here is that, you know, the LIGO detection was the collision of two black holes. So we literally, we watched two black holes crash into each other out in the universe. And then we expected that they should be producing a wave of gravity, right? And we detected that wave of gravity. We detected that ripple in space-time moving across us. But really, astrophysically, it's the equivalent of seeing two semi-trucks crash into each other 10 feet from your head. And then you say, yeah, I heard that. I heard they made a noise, right? I mean, it's such a massive, massive interaction that happened right there. And we barely detected it, right? Well, we felt a little bit of it. And so, again, we are really not good at detecting and measuring these things. And again, we were using a laser that, you know, a very precision laser grid that is kilometers long to detect this. And so this is right on the edge of our ability to understand such things. You know, we had one of these interferometers here in Louisiana and one up in Washington State, and then another one actually over in Asia. and we can detect the wave moving across the planet. But again, it's only the tiniest of wiggles as we understand it. And so we're not very good at really describing or manipulating these things yet.
My students are always asking me when we're going to go to Mars. Are we going to go to Mars?
Yeah, we are working on going to Mars right now. Yeah, we are working on going to Mars. We need to learn to honestly get to the moon, in my opinion. We need to learn to get to the moon and live on the moon, right? As we went to the moon in the 60s and 70s, we went to the moon for a few days and then came back. And we were never farther than 3 or 4 days from Earth. Going to Mars is going to require, with our current propulsion technologies, going to Mars is going to require being in space for at least 6 months to a year one way, right? And so it's going to take, you're going to have to be in space for long periods of time. And we do not currently have the technologies to be in space. The longest anyone has been in space aboard ISS is a year, right? And in a year, we have, even in low Earth orbit, we have significant health effects that never mitigate, right? That you are permanently changed because you have been in space for that long. And so going to Mars is going to require the ability to live in space for at least about 2.5 years. And we're not there yet. We can't have someone, even in LEO, right? Even in low Earth orbit, you're still inside the Van Allen belts, inside the radiational field of the planet generally, that is shielding you from deep space radiation, from all these particles, from all this high energy that is happening out in the universe. And so outside, away from the planet, we're going to have to figure out ways to mitigate that better. We're going to have to figure out ways to mitigate the gravitational impacts and of being away from the planet's gravity. And so in doing that, right, I mean, we're going to have to figure out new methods to allow us to do that. And I think that a big part of that is going to be living on the moon for longer terms than a couple days, really getting a base on the moon where we can go to the moon and live for months or maybe years. And then that will give us the resources and to give us the scientific knowledge and understanding needed to go out to Mars. But as it exists right now, there are big gaps, just from a human perspective, in our ability to keep someone alive in space for that long. And we need to work to fill those gaps.
Chris, we have a question in the chat that says, could you maybe talk a bit about the future of space exploration and international cooperation?
Yes, absolutely. Yeah, so we are currently working on the Artemis program, as you may have seen. We have just recently sent a vehicle out around through cislunar space, out around the moon, and then came back. It took about 25 days. And we are working towards doing that now with people aboard. We're going to do Artemis 2, which should be happening in approximately 2 years, and we'll have a human crew on board that will go out and do that. They'll go out and fly around the moon. And that will be followed by Artemis 3 about 2 or 3 years after that, which will actually land on the moon. And each of those missions is going to have an international crew. We will have members from Canada, we'll have members from Asia, from the European Space Program, from the Japanese Space Program. And we are working even on Artemis 1, the service module, the back half of the vehicle was mostly manufactured by the European Space Agency. And as we do these things, I mean, even the space station right now, half of the space station is Russian and half is the USOS, what we call the US operating segment. So is US and Canada and Europe and Japan working together. And so even now, with the geopolitical tensions that are going on, we are still partnered and we are still working very closely with the Russians on a day-to-day basis to keep the space station going. And that's really a great thing for all of us, and a great thing for humanity as a group, is that we are working together as we go out into space, as we go out to the moon, as we go out to Mars. These are going to be international missions. These are going to be missions with diverse international crews, and it's going to require international cooperations and really utilization of resources that are beyond the scope of any one country and are going to be, really Earth people resources, not just one nation's resources. And the more we work toward that, the more we work toward using our resources as collective humanity rather than as just just as nation states against each other, the better it is for all of humanity, because really, again, we are all just together on this very, very small speck in the vastness of space. And the better we learn to work to get along together on this speck, the better we learn to cooperate to take care of this speck, the more it's going to improve all of our situations as human beings.
So Chris, I heard with the phasing out of the International Space Station the next couple years, is there plans to like replace that? Is it just it's old and we want to make it a new one, or is the Artemis taking over that, permanent
so we are
space?
We are absolutely planning to keep our hold in LEO and low Earth orbit. Currently, the plan right now is working on a series of commercial space stations, working on having commercial entities build their own space stations. You may have heard of some of the efforts by companies such as Blue Origin, such as Axiom, that are working on these partnerships to build their own commercial space stations, which then NASA will use as a service. And so that's the plan for the future of space stations in low Earth orbit, is to have them be commercial entities that are run by commercial companies, similar to how right now we have SpaceX providing commercial launch services to the International Space Station, right? We have crews, NASA government crews flying on commercial vehicles on a contract basis up to the International Space Station and back. And so we are working to expand that model out into low Earth orbit and creating these commercial orbital platforms. And so the plan is, as ISS ramps down, to start ramping up these commercial orbital platforms and really make low Earth orbit much more of a commercial available and a commercially viable environment for everybody. And then again, as you said, for NASA, then we would go out to the Artemis program, out to the Gateway program, which we're talking about we're planning to have a space station that is orbiting out in cislunar space now, the orbital gateway. And that will be the next NASA station out beyond low Earth orbit, out in cislunar space. And so the idea is to start transitioning these capabilities to the private sector, to the commercial sector, and then have NASA keep kind of paving the road and keep developing more capability out into space.
Cool. When do we get a space elevator? Is that in the plans too, or is that still too?
A space elevator, yeah. That is one of the things where, yeah, you're looking at the intersection of engineering and really material science. Because while a space elevator, would be really cool, we currently don't have the materials that would allow us to build such a thing. And so, yeah, I mean, that's if we can figure out the material science for that, then absolutely that is something we could do.
Hi, I have a question. My students like to ask me about things like wormholes and white holes, which I have to admit, I don't actually even know what that is.
Okay.
And I was wondering if you could speak about those. Do they actually exist, or is that just something that we predict might exist?
Yeah, so that's a question, right? So the answer to that is more toward the prediction than the existence, right? So again, at this Schwarzschild radius, at the event horizon of a black hole, we don't know what is happening beyond there, right? Really, our equations break past there, and also our ability to quantitatively observe what is happening past there also doesn't work, because our understanding of space and time no longer exists past that point. So we can't look in there with a telescope and see anything. Right? We can't directly take measurements of what's happening in there. So yeah, so to answer the two different parts of your question, it is possible there is a white hole on the other side, right? It is possible that everything that's going into the black hole is getting spit out in an opposite set of equations, right? It's possible that if you think about all these equations as collapsing as they hit that point, they may expand back out symmetrically on the other side, in which case there would be a white hole on the other side. There would be something on the other side spitting out all the stuff that went into the black hole with a opposite set of physics equations. And that was what we would call a white hole. It's also possible that there's a wormhole there, right? And that's, it's possible that there is the black hole goes into another black hole on the other side that you could go in and then pop out of the other black hole. And who knows where the other black hole is? Maybe it's in another universe. Maybe it's in a different part of our universe, right? And so that's when you're talking about a wormhole. You're talking about drilling a hole through space and time to another point in space and time, such that you can travel through space and time without actually traveling through space and time, if that makes sense, right? That's kind of the model of bending a piece of paper and then punching a hole through it so that you end up on the other side of the piece of paper without traveling across the entire paper, right? And so that's where you're talking about a wormhole, right? It's possible that where all these equations zero out, you would then have no basis. You would have no base for those equations, and you could just move to another black hole anywhere you wanted and just jump back out there. But again, those are theoretical. Those are things that are in the realm of science fiction or in the realm of very theoretical science math right now that we don't really know. Then that is a question of something I tell students all the time is, if this is stuff you are interested in, study it, learn about it, go absorb everything you can find about it. Maybe you will be the next great breakthrough. You will be the person who describes this in a way that people haven't currently thought of, right? And you will be the person who, yes, does discover, actually shows that there are in fact white holes. I mean, even before we took this picture, we had hypothesized that there were black holes. We had measured things that told us there probably were black holes, but we never actually taken a picture of one. We never actually seen one before. And so, this picture, and again, was taken by a grad student, a team of people, but led by a grad student, someone in their 20s, who showed us this, right? And this is stuff that really fundamentally changed science. And so, yeah, I mean, this is, I would tell your students, if they are interested in this stuff, absolutely study this stuff.
Thanks.
So I have a question. Myself is Praveen Khosla, and I teach at middle school, first of all, and I'm math and science teacher. And I got this opportunity to attend your PD today, and I'm very fortunate to hear from you, especially since you provide your services to NASA Space Center and the best resource to ask this question. Students at this age of 12 and 13, like I'm teaching 6th grade math and science, and I find that the students are not interested because of the high vocabulary and the difficult stuff in Arizona. So I just want to ask you, how do we have any resources like at NASA website, so we can show the students the videos or the articles or whatever is available, so that can motivate students towards science? Because
there are.
So we have those resources.
Yes, there are. I can find some of them and send them to you. But yes, there are NASA educational resources. NASA has an Office of Educational Outreach. And so, yes, there are, if you look for the NASA Office of Educational Outreach, there are pages of resources, and I would be glad to provide some of those to you, and I would be glad to kind of help you find some of those if you would like.
Because what we find these days, it's a subject, like I know today's PD is just an initiate to prepare teachers for STEM. Mm-hmm. And that's why I am here. And I see that all the content is a little bit higher level. But since I teach 6th grade, we have that matter and gravity and everything, so we can teach them. But the thing is, they should be getting motivated before we provide any content to them. Right. Mm-hmm. So I was looking for like some resources like everyday video or something, so they get to, have that curiosity, about science. That is what was my questions. And you said, yes, we do have resources. And I would definitely like to, I think I see one that you have shared right now. All right. I see that nasa.gov HP education. Okay.
Okay,
Thank
yes, so yeah, I didn't share that, but whoever shared that, thank you.
I think if this is making sense, like I know everybody is talking about the higher level of content, and I was thinking like the students in Arizona are becoming like, oh, no science, no science. So we should find something that can motivate them to, in order to go and proceed forward towards this content area.
Mhm,
Thank you so much.
absolutely. So
I'm
any
gonna
other
s-
questions?
I'm going to say last call for questions. Okay, it sounds like that might be, we might have answered all the questions we have right now. I don't know how best to thank Chris for being here today, but we're virtual, so can we, there's virtual clapping, there's. all
Thank you, I
kinds-
appreciate it.
We can turn on our cameras and clap. We've got lots of thank yous coming in through the chat if you want to go down there and check those out.